In this video, we will go over how to train logistic regression. To implement logistic regression, there are a few requirements that need to be met. We've seen how we can represent an input as a vector of features. We've seen how the function of a neuron can be used as a classification function to calculate the probability of a certain label, and how a decision boundary can help us determine the predicted class based on that probability. We've seen how the loss function can measure the difference between the predicted label and the true label. And we've seen how we can use gradient descent to reduce the difference between the predicted label and true label. Now that we have all the tools we need to train logistic regression, let's walk through the steps together. We will do the following steps for some number of iterations. This can be an arbitrary number, and the number of iterations is referred to as a hyperparameter. A hyperparameter is any parameter that we adjust between training sessions to attempt to improve training. First, we will take a random training sample out of our training set. This randomization will ensure there is no extra influence from the set being sorted in any way. Lastly, we will update theta, our weights and bias, using the gradient of the loss function with respect to the weights. See the video on gradient descent for a refresher on what the equation would look like. We encourage you to try and code this in a language of your choice. So let's train logistic regression. We will start off with the weights of 0 and a bias of 0, a completely untrained model. We are given a set of training samples. Let's say we randomize the list of training samples. Now we select the first training sample. The feature vector is 3, 1, 0, and the true label is 1. We also need to keep track of the learning rate for our calculation. Let's say the learning rate is 1. Now we are going to update the weights and bias using gradient descent. Let's focus on updating the weights for now. We'll come to the bias later. W at the current time step is a vector of all zeros. The learning rate is 1. Now let's plug values into our gradient. We can plug in the true class 1 and each of our features. The bias is 0. Plug in our weights and feature vector, and now calculate the dot product. 0 times 3 is 0, 0 times 1 is 0, 0 times 0 is 0. Adding those zeros together gives us 0. Now we apply the activation function, in this case sigmoid. The sigmoid function is 1 over 1 plus e to the negative z, where z is 0. E to the 0 is 1. 1 plus 1 is 2. 1 divided by 2 is 0.5. 0.5 minus 1 is negative 0.5. Each item in our vector is a multiplication of negative 0.5 by the corresponding feature in x. Calculating that, we get a vector of negative 1.5, negative 0.5, 0. Since we are subtracting the original weight vector and our newly generated vector, we get 1.5, 0.5, and 0, which will be our new weights vector. Let's keep hold of that information, and now let's calculate the new bias. Let's plug in b at the current time step. B is 0. We can plug in the learning rate, which is 1, plugging in our true label y, which is 1. We can now plug in our weights and feature vectors, and then calculate the dot product, which we know is 0. And the sigmoid of 0, as we calculated previously, is 0.5. 0.5 minus 1 is negative 0.5. So our new bias is negative 0.5. Now that we calculated the new bias and weights, let's update our current weights and bias. Now we can use our new weights and bias for the next step in the training process. We would then select the next training sample, which has a feature vector of 4, 1, 1, and a true label of 0. We will leave calculating the new weights and bias as an exercise for the viewer. These videos were inspired by Josh Starmer at StatQuest. Be sure to check them out.